Hello friends and students, welcome to the e-learning of on the topic superconductivity. Superconductivity is a state of matter which is exhibited at low temperatures. The resistivity of the material comes to 0 at low temperatures, and let us see the superconductivity phenomena, the theory and applications. First of all, resistivity of a normal metal. So, usually we have in a metal we have free electrons, and these free electrons are the major thing for the conductivity in the metal. And what is the resistance in the metal? So, resistance is nothing but these free electrons are moving inside the atomic lattice, and they have scattering with the atomic lattice ions. So, because of the scattering, the kinetic energy of the electrons are transferred to the atomic lattice, and therefore, that is dissipated in the form of heat. So, and if the temperature of the material becomes is increased, the lattice vibrations becomes more pronounced, so that more scattering events taking place. Because of the more scattering events, the dissipation of heat will become more. So, this property of the energy transfer from a kinetic energy of the electron to heat energy, and in that way the decay of the current is called as resistance. So, you can see that the graph between the resistivity and temperature, the resistivity, and this is the low temperature. If you reduce the temperature, the resistivity decreases. So, what is the resistivity? Resistivity is the electrical resistance per unit length and per unit cross sectional area. So, rho is equal to R A by L, where A is the area of cross section, L is the length, rho is the resistivity. We can see that the resistance at low temperatures, the lattice vibrations will be minimized, and therefore, the scattering events will become decreased. Okay. So, because of the less scattering events, then the more dissipation of energy is reduced. So, by the way the resistance becomes decreased, and we can see that at a point at 0 Kelvin, that is at a very low temperatures at 0, the resistance of a normal conductor does not come to 0. There is some resistance that is called as residual resistance, and this is because there are impurities and imperfections in the material that will cause the residual resistance. So, there are we can see that we can classify or we can differentiate metals, semiconductors and insulators by the resistivity. So, resistivity of metals will be in 10 power minus 2 to 10 power minus 8 ohm meter, and for in the insulators which are having very high resistivity, which is in the range of rho is equal to 10 power 11 to 10 power 19 ohm meter. Semiconductors, which is lying between the metals and insulators, so they will be having a resistivity in between the metals and insulators. So, that is 10 power minus 5 to 10 power minus 6 ohm meter. So, this unique phenomena, that is superconductivity, was first found out by Dutch physicist Kamerlingh Onnes, and in the year 1911. So, the superconductivity is a state of matter exhibited usually at a very low temperatures, where the resistivity drops to 0. And what happens is, when you lower the temperature, he observed that in a pure mercury, when the temperature is near to 4.15 Kelvin, the resistance abruptly come to 0. The resistance abruptly come to 0. In case of conductors, there was a residual resistance, but the resistance in case of mercury in a pure metal abruptly come to 0 at 4.15 Kelvin, and he was surprised by this phenomena and named this particular phenomenon as superconductivity. And therefore, what happened is people started to work in some other metals. So, other metals which should have a different the transition temperature. So, the transition temperature from a normal conductor to a superconductor, there you have a critical temperature, that is Tc, T suffix C. So, Tc, transition critical temperature, is a temperature less than the critical temperature becomes a superconductor, and the temperature more than the critical temperature, it becomes a normal conductor. So, the properties of semiconductors, we can see that it exhibits zero superconductors, it exhibits zero electrical resistance. It means that if you have a superconducting loop coil which is placed in a magnetic field, and if the temperature of this particular loop is reduced below the critical temperature, and suddenly if the magnetic field is switched off, a current will be induced into the superconductor. So, current will be flowing into the superconductor, and if for a change in decaying current, we know that the current as a function of time with a finite resistance is given by I is equal to I naught into e power minus RT by L, where L is the inductance. So, how to measure a zero resistance? Zero resistance we can measure with some instruments that this measure it is exhibiting zero resistance. So, what we have done, what Owens have done is, he used a test coil. Okay, he used a test coil near to the superconducting ring, and if there is a change in this superconducting ring will have a current flowing through it, and this current will be constant. It is not going to change. So, it is going to be there. So, because of this constant current, there is a constant magnetic field. Understand? Constant magnetic field, and because of this constant magnetic field, it will induce some flux. It will induce an EMF to a neighboring coil. So, and this if there is a change in the magnetic field, it will induce the EMF in the test coil. But here, the superconducting coil, there is not going to be a change in magnetic field, because the current is persistent current which is there for a long time, and therefore the magnetic field will be a constant. So, there will be no change in the magnetic field, and because of that, there will be no EMF induced in the test coil. If there is an EMF induced in test coil, then automatically we can understand that the resistance is induced, or the current is going to be decreasing, and it is not going to exhibit a superconducting property. So, now with this having a test coil, the zero electrical resistance have been understood. And what is a persistent current? So, another very important property is persistent current. The current is not going to decay, and this current is there for a long time inside the loop, and this current, for a steady flow of current, we require a external energy source, a voltage. We are not going to apply a voltage in this case, and therefore, this current is not it is going to be there for a long time. It is 10 power 5 years, quite a long time, without any external source to drive it. And there is because of this steady current, there is a steady, the constant magnetic field is also there, and this is called a persistent current. Critical temperature. So, critical temperature is the temperature where it distinguishes or differentiates between a normal conductor to a superconductor, and the critical magnetic field. So, you can apply an external field, magnetic field, and this magnetic field will destroy the superconducting property. It will destroy the superconducting property to a normal conducting property. So, there is one particular magnetic field that is called critical magnetic field, and if this critical magnetic field is applied, it will change the superconducting property to a normal conducting property. So, the relation between a critical magnetic field to a critical temperature is given here, where Hc is a critical field at a particular temperature is equal to Hc naught, that is the critical temperature at 0 Kelvin into 1 minus T by Tc square. So, this is a relationship. You can see that this is a relationship between temperature and field. So normally we have a transition temperature or the critical temperature, where in which you have the transition from a normal conductor to a superconductor. But when your field is increased, when external field is given, for example, when the field is Hc2, then automatically we have to still go to lower temperatures. The critical temperature goes to a lower temperatures, and therefore it shifts to Tc2 here. Again, if you increase the magnetic field, then it shifts to Tc1. So finally, at 0 Kelvin, we have the critical temperature with critical magnetic field at 0 Kelvin. So this is the graph indicating the relationship between the magnetic field and the temperature. And there is one more thing, is that we have a current flowing into the superconducting loop, and this current, there is the amount of current should be flowing into the superconducting loop, so that it can be staying for a long time. If the current is having a critical value, that is, if it reaches certain critical value, what happens is it generates a critical magnetic field, and that in turn, the internal magnetic field will destroy its superconducting property. So that is a very crucial thing. That is, an external magnetic field is not required. An internal magnetic field itself is used to destroy. So that effect is called as Silsby effect, which was found in 1916. So that gives a relation between the critical current and the critical magnetic field, where IC is equal to 2 pi R into Hc. So this graph indicates the three things, that is current density, a relationship between current density, critical magnetic field, and critical temperature. Another very important effect is the Meissner effect. So we can see that here the Meissner. So this effect was during 1933, and Meissner and Oeschenfeld, that is two German scientists, they have been working on this thing, that if you have a superconductor, and if you apply a magnetic field, the magnetic lines of force will pass through the conductor, normal conductor, when the temperature is more than the Tc. But what happens is, when the temperature is less than the Tc, when T is less than Tc, the material will repel, or it will not allow the lines of force to pass through the material. So there is a B inside the when temperature is more than Tc, but B value, that is the magnetic induction, becomes 0 when the temperature is less than Tc. So the relationship between magnetic induction and external field is B is equal to mu naught into M is intensity of magnetization plus H, that is the externally applied field, magnetic field. And since B is equal to 0, therefore what happens is mu naught is equal M plus H is equal to 0, M is equal to minus H, and M by H is equal to minus 1, that is susceptibility is equal to minus 1. Susceptibility having negative values is diamagnetic materials. So a superconductor is exhibiting a diamagnetic behavior, and this is one critical thing to understand about a superconductor. So superconductor has two main things. How to identify it is a superconductor, that is, the resistance should be 0, that is one point, the first point. Second thing is, it exhibits diamagnetic property. So Meissner effect is used to test whether this material is a superconductor or not. First thing. The second thing, this property, that is the repulsion of magnetic fields from a material, is a unique property, is in a way that there is an application called maglev, that is magnetic levitation. So by that you have maglev trains, and this is one reason, the advantageous thing for Meissner effect. To understand what happens at temperatures below Tc, at low temperatures like below 10 Kelvin in pure metals, three scientists, that is Bodin, Hooper, and Schiffer, they gave the BCS theory. Bodin, we know that he was awarded Nobel Prize twice, and these three people received their Nobel Prize during 1972. So what they proposed in this theory was you have to understand one thing. The in a normal metal we have electrons, and these electrons are called as, in a normal conductors we have electrons, and these electrons are called as fermions. They accept the, or they obey the Fermi Dirac statistics. So they are called as fermions, and they obey the Pauli's exclusion principle. So not more than one electron will have these 4 quantum numbers, is the Pauli's exclusion principle. So that was the case of normal conductor. So in case of superconductor, what happens is these fermions are converted into bosons. So now we are talking about bosons in stuff which obeys the Bose-Einstein characteristics. So what happens is, in an atomic lattice, consider this is a copper lattice or something like that, and in the atomic lattice the electrons are moving into the positive ion lattice, and because if one electron is coming inside that lattice, and this electron is, because it is moving, because there is a positive terminal here, when you apply a voltage, then the electrons are moving from one place to another, that is moving towards the positive terminal. And what happens is, when the electron is coming here, it will attract the ions. It will attract the ions. So we can so this is the metal, for example. You just consider this is the metal, and you have the ions. Okay, so you have the positive ions in the metal, so now you have an electron here. So there are electrons. So what happens is, when you apply when the electron is here, this electron will make the shift in the atomic lattice, and because of this, what happens is, a larger positive, a creation of a larger positiveness inside the lattice takes place, and this is temperatures below Tc in metals. So when temperatures are below Tc in metals, the electrons are inside this. So these electrons will attract the ions, and this will become a positive, a larger positive thing which inside the lattice, and this will in turn will attract the other electrons towards it. So these electrons are attracted towards this. Well, the temperature is less than Tc, and what happens is, because of this, the lattice movement, that is the phonons, the electron, normally electron will repel another electron, okay, but here this electron, in assisted with the phonon, will attract, there is a pulling of another electron. So electron interaction happens with phonons. So phonon is a boson, and these coupled, that is the pair here, that is called as Cooper pair, because Cooper proposed the idea, so it is called Cooper pairs. This Cooper pair is nothing but the electrons. Even the electrons are at long distances. For example, it can be more than 1 nanometer, more than a nanometer distances. So it can be large distances. This pair can be formed. So these pairs, these two electrons will form a pair, with the phonons, and they will move. So what is the advantage of this? See, when it becomes a boson and the phonons are there emitted and the Cooper pairs are bosons, they even lot of Cooper pairs can occupy the same quantum state. That they not obey the Pauli's exclusion principle. So here what happens is you don't have any scattering effects as we found in free electrons, which are fermions. Because of the scattering we have a resistance, but here the scattering effects have been nullified in case of Cooper pairs. So these Cooper pairs are moving from one place to another without any scattering, without any energy loss. So that is the thing that we have to understand. So without that, so they propose this theory, and particularly this is for superconducting phenomena which is exhibited at low temperatures, that is below 10 Kelvin. There are high temperature superconductors, but they are not they don't have any convincing theory to explain like BC's theory for low temperature superconductivity. So there are two types of superconductors. There is one is type 1 superconductor and type 2 superconductors. As we found out how to differentiate, when you apply a field, when you apply an external field, and this external field will destroy the superconducting property. So consider this is a superconducting property and this is a normal state. So you apply a field, so the internal magnetization takes place, that is mu naught m will increase, and that in turn will destroy the superconducting property to a normal property. So type 1 superconductors, they are called as soft superconductors, and they exhibit a complete Meissner effect, and they exhibit a perfect diametric property because they have an abrupt change from a superconducting to a normal conducting stage. They are called as soft superconductors, but the thing is the magnetic field from these materials are lesser, like 0.1 Weber per meter square, and examples are like we have lead, zinc, or these are the materials for type 1 superconductors. Type 2 are superconductors like niobium, and these superconductors are they don't have the complete Meissner effect, or they do not have they are not a exhibit diametric property, complete diametric property. And we can see that there is one critical temperature for type 1 superconductor, but they have two critical temperatures for type 1 and type 2. So we have a mixed state here, and this mixed state will have both the superconducting state and also the normal conducting state. So another important property during 1962 is by Josephson, that we have a superconductor, we have another superconductor, in between there is a 1 nanometer thickness insulating layer. So when two superconductors are separated by an insulating layer, these one superconductor it will have a Cooper pair, and another superconductor will have a Cooper pair, and these two Cooper pairs will have a phase difference between among themselves, and because of this phase difference and this a super current flows through the insulating layer from one place to another, and this super current Is is equal to Ic, that is the critical current into sine of phi naught. So this is called as DC Josephson effect. DC Josephson effect is nothing but two superconductors separated by one insulating layer of small thickness, say 1 nanometer or less than that, and the Cooper pairs they have the waveforms they have a phase difference between the waveforms from one side of the one semiconductor Cooper pair and the other semiconductor Cooper pair, and therefore because of that a current flows, that is called as DC Josephson effect. And if you apply a DC voltage across this, what happens is then AC Josephson effect is observed, and you can see that an additional phase difference is carried out, that is del phi, and by TDS, I mean like by the quantum mechanical calculations, we get it del phi is equal to 2 pi t into 2 eV by h bar. 2 eV is nothing but the energy difference between the Cooper pairs of one superconductor with the other superconductor on the other side of the insulating layer. So that is the energy difference. So the I is equal to now IC sine of phi naught plus 2. You can substitute, instead of del phi, you substitute this value here. So the AC dose upturn effect is nothing but if you apply a voltage across the two junctions, then DC voltage, then a current, AC current has been given, and that frequency of that AC current is nothing but mu is equal to 2 EV by H. So the one important application of the Josephson effect is the SQUID, that is superconducting quantum interference device. SQUID is superconducting quantum interference device. So this is a SQUID. So how to understand a SQUID? So you can see that a SQUID, in a SQUID, we have okay. So we have two parallel Josephson junction. We have two parallel Josephson junction, that is one is P, another one is Q. Okay. So what happens is when we apply a DC current, and for example this is this point is C and this point is D. So when we apply a super current which is flowing from C to D and which passes through P, this is one Josephson junction and this is another Josephson junction. So the super current, that is the Cooper pairs flowing in this direction, and after tunneling through this barrier, okay, so it will reunite. These two currents will reunite with one another and they will come to D. So what happens is this is like a double slit experiment. So you have a double slit experiments where we have the light flowing through the two slits and then diffraction taking place, and this diffraction bending of waves will again interference and then form interference fringes on the screen. Similarly, here what happens is the Cooper pairs are like waves, and these waves are moving, they are splitted into two directions. Say this is A, branch A, and this is branch B, and this is this particular wave is moving in this direction, and this particular wave is moving in this direction. So this is tunneling in the superconductor, and again this superconducting junction, this is formed by niobium based materials, or lead based superconductors can be used. Niobium with the 10% gold and niobium oxide as the insulating layer. So back electrode can be niobium and front electrode can be lead alloys. So like that, this sandwich structure is the Josephson structure, and the quantum mechanical phenomena when it is moving, when the waves passing through this, tunneling through this and reaching D. So there is a phase difference between C and D, and this is del A, which is choosing the path along P, and there is a phase difference between C and D when it is passing through Q. So that is delta B. So normally if this arrangement is not in a magnetic field, then delta A minus delta B will be equal to 0. So there the net difference will be equal to 0. So in case if we have when it is when a perpendicular magnetic field is induced into this particular superconducting quantum interference device QUD. Okay, so this particular magnetic field, a feeble magnetic field, it is not a big magnetic field, it is a very feeble magnetic field, and that will induce a phase difference. Okay, so that will induce a phase difference, and therefore the tunneling current IT is equal to 2 into I naught sine delta naught into cos E phi by h bar c. So this is expression for the tunneling current here, and we can see that by a small magnetic field, a feeble magnetic field, there will be a potential difference across the terminals C. So this is a magnetic field converted to a voltage. So flux to voltage converter. So very small voltage can be generated, and we can measure the magnetic field. So feeble magnetic field can be measured. So this is how this is. So flux to voltage, let's say transducer, a very sensitive magnetometer, and it is used in engineering and medicine fields. As we pointed out, it is used in MRI, magnetic resonance imaging process, and geologists used to see in continental drift and rock magnetism. Magnetoencephalography, that is, it is used to measure the heart and the brain waves, magnetic waves. That is, it is in the term of 10 power minus 14 Weber per meter square. So such small magnetic fields can be measured by using QUD. So non-destructive testing, in case of flights, we have the aluminum plates, it might have corrosion. So riveted aluminum plates, we have corrosion. So to test from the conductivity experiments, we can find out the nature of the riveted plates. So another very important thing is the high temperature superconductors. That is very crucial, because from 1911 to 1986, people have been working on low temperatures, that is less than 10 Kelvin. But after the discovery of and that too, we can see that lanthanum, barium, copper oxide, that is insulators. As we discussed about, we cannot make a good person to a Superman. We can make a bad person to a Superman. So there are a lot of stories we know that from a thief has converted to a saint. So a transition from a very bad person, for example, Valmiki. So he is a thief and you convert into a good person. So some analogy, just for a lighter sense, you just take it out. It is really observed in materials also. That is, in normal temperature, there are very good insulators, oxides. But when the temperature is decreased, when well below the when the temperatures are like 30 Kelvin, they exhibit a superconducting property. And that is a crucial thing. That is the first thing they observed is lanthanum, barium, copper oxide by Muller and Bernardsdorff. They got Nobel Prize for this. So that's a very important discovery, because superconducting phenomena at higher temperatures are a very important thing because for practical applications. But here we are mentioning higher temperature is minus 250 degrees. That is what we are talking here. So these are the various superconductors. You can see that mercury during 1911, and these are metals initially, And there was a crucial thing happening here is lanthanum barium copper oxide by Muller. And very surprisingly is 1987, that is a very another crucial thing is 1987, that is yttrium barium copper oxide by, and it's a because it can be worked with liquid nitrogen, because liquid helium is very costlier. So all this until 1987 the materials have been used with the liquid helium, but after discovery of yttrium barium copper oxide, then it turned to have liquid nitrogen, which is cheaper. So that is the thing. And several copper oxides and iron based materials have been researched these days. And so this is the superconducting timeline. So superconducting magnets, so what is the important thing is the normal conductor, if you pass heavy currents means in terms of thousands of amperes, the material will melt. So the material cannot withstand, and also the cost involved will be more. So to reduce that, to make a safety procedure, we have superconductors where which you can go to a very high current. And what is the need for the current? The need for the current is to make a high magnetic field, give a high magnetic field. So that is the way that the superconducting magnets have been produced, and they are used in different applications in NMR and particle accelerators, CERN particle accelerators they use there, and maglev trains. So this is how the donut shaped MRI which has the superconducting facility, and which generates 3 Tesla field, which is a very high which is a magnetic field of this level. This is only achieved by superconducting materials. So the one application is the maglev train. So we have each and every carriage in a train is having a superconductor, and the path we have the aluminum track, aluminum path which is having the rails which are having the superconducting coils which is connecting electrical current, and that in turn produces a magnetic field. And these two magnetic field, as I pointed out earlier, this is a application of Meissner effect, and because of this Meissner effect the trains will float on the rails, and to 15 centimeters for example, few inches they will be there, and then initially these wheels will be there on the rail, and once if it is started up, it rises up and then it moves, and like an aeroplane, when it comes down to a stage, then the wheels are retractable and they fit in on the rails and then they move. So this is how the thing is. So this image shows that you have a pull and push. So we have a north pole and south pole. So north and north will repel and south will attract. So in that way, that the train is made to accelerate, and we can achieve achieve 500 kilometers per hour. So this is one important thing that we have to understand. So thank you very much, students and friends, and this is a nice time to discuss about the superconducting property, and we discussed about the superconducting materials, different types of superconducting materials, and still people are working in this area, new materials, and let us hope this superconducting phenomena will be utilized in a near future. So thank you for active listening.